welcome, or sorry, I have to do it in English, of course. Welcome to everybody here to this session about SDN and open flow. It's of course interesting that it is about networking that we are going to talk about, and I understand the wireless network is not functioning. So in principle I already have now a problem that I don't know who's going to speak, because I was expecting to utilize the website to know who's going to speak, but luckily I have some memory. I got some cached web pages on this laptop from somebody else. Is it working again? Okay, thank you for that. But at least this is a session about software-defined networks and open flow and applications about that. So there will be 3 speakers. First of all, it is we are going to hear from Manfred, and he will say most of it about, let's say, the optical layer, the lower layer. So it's very interesting to see that aspect, I think, of SDN and OpenFlow and how they can be combined. And Manfred will be the first one to come on the floor. And then we get Ronald van der Pol, who will talk about the multipath TCP and how it can be utilized. And together, then Michael at the end will also give more insight on the aspects around multi-protocol TCP, multipath TCP, for instance. And all that is using SDN/OpenFlow. So I would like to give Manfred the floor. He has been very active in networking, mostly the optical layer, and he's working for Coriant, which is the follow-up company for Nokia Siemens network. So the floor is yours. And we'll have, let's say, 25 minutes for each session, and then 5 minutes questions in the next presentation. So there you are.
Thank you, Victor, for this nice introduction. It's amazing that you can work for three companies, so Siemens, Nokia Siemens Networks, and Coriant in your career without changing or quit your job only once. Yeah, so it's. That's a good achievement, I think. Okay, as you can see here, we have done this work together with Nokia Siemens Networks. Therefore, you see Nokia Siemens Networks and Coriant here on the bottom. Most of this work has been done still in Nokia Siemens Networks. So I'm going to tell you a little bit about SDN-based packet optical transport system. And it's one of my favorite topics because it looks at how you can improve the interworking with router networks and get the cost down of the overall networks, especially the core networks, and make it more scalable and more green. The agenda you can see here, just 4 points. Why packet optical transport and SDN. Then SDN-based packet optical transport proposal for core networks. The current development status and demos, and summary and final remarks. Yeah, SDN is an important research topic in Coriant and also in NSN. So here I've touched only the topics which are important for Coriant. Of course, transport network virtualization and transport as a service is one of the applications which we have discussed already for many years, but up to now has not really been realized, and we hope that this time it may be realized. Then data center connectivity is a hot topic since Google talked about this heavily and was responsible, I think, to a large extent responsible for creating this hype around SDN. Then, of course, one of my favorite topics is this multi-layer networking and optimization, which then really provides the cost reduction and the energy efficiency and scalability of the future networks. Then, of course, we should not forget in networking that, especially on the optical layer, the flexibility is increasing. Well, I would not say too fast, but at least it is increasing. And it is also now more and more used and will be more and more necessary in the future with the high data rates to come. And then the packet optical, packet optical integration and interworking. That is the topic which I mainly discuss here. So we see, or we are working towards this evolution, basically virtualized dynamic multi-layer packet optical transport networks, and we have a product there which has been released already to a big customer, which is called IOC, Intelligent Optical Control, and that is also the basis for our SDN platform, but we think it goes beyond the current focus of SDN. Then integrated packet transport, so integrated better interworking with routers, and then finally the core router consolidation with pods, because we believe that building the router networks or the core networks in a hierarchical way with all these massive multi-chassis core routers in the future is not the right way. We propose to have here really, or using SDN to build a fully meshed PE router network, basically. And this is what I'm going to present. So it's just a fraction of the overall work which we are doing. So previous attempts for packet optical integration add control plane and management complexity and have failed up to now, and this has been also by the founders or the most promoters of SDN. It has been explained many times why the peer model, the overlay models and the augmented border peer models have failed up to now. Well, there is still some work on this one, but nevertheless, it's very, well, I would not say complex. It's not easy to implement this in the current organizational issues, structures. So the major issues is that reusing and extending MPLS protocols for GMPLS adds complexity. Takes very long to standardize this, more than 10 years. We need to solve the interworking between IP MPLS and GMPLS control planes. In principle, it should be simple, but when you look at reality, it isn't really simple. So I haven't understood why it is so complicated, but probably also because of the organizational issues and also of the market interests. And that's why still hierarchical IP MPLS networks with some bypassing starting now are built. And the full argument is they are built only because of the control plane. They are not built because of the data plane, they are built because of the control plane. And the question always is, why do you throw so much money away for the control plane? And without getting any benefit for the data plane. Well, and nevertheless, also being forced by these control planes, transport networks run GMPLS mainly for restoration purposes today, and this trend will continue, and it may even make sense to run it in parallel with SDN-based networks for restoration purposes. If everything fails down, then the GMPLS will find a way to at least use the remaining surviving resources. Yeah, our SDN-based POTN proposal for core networks looks very simple. We have the IP MPLS networks in separate domains, and the POTS domain also separately, and the POTS domain is controlled by an SDN controller. And we propose to have here IP MPLS NNI interfaces. Now the key architectural proposals are to have IP MPLS and POTS in different administrative domains, to have a logical or virtual full mesh of PE routers via the POTS core. Of course, a strict separation of client and POTS control and data planes. That is one of the reasons why in IP the problem always start, because IP controller and data plane are not fully separated, or not so separated from each other. Then, as you can see here with this little indication of a router, using centralized routing in an SDN controller, this is something which has been also proposed since many years and is now being investigated by many, organizations, research organizations, but also in industry. And we have done also some tests on this, as I will show later. And then using for the control plane just the minimal number of routing protocols for interworking between these domains, between the router domains and the POTS domain. And this is in line with the seamless MPLS approach also, where they have also produced guidelines to minimize the number of routing protocols for building scalable IP networks. And we are doing here, following here basically the same principle, but in a different context. And then, here the POTS domain then with an SDN controller, which is pretty simple to build, I would say, because centralization in transport was always the case. So we can reuse their number of software which we have anyway in our hands and developed previously. So, and then we can do here the multi-layer optimization also by using different technologies from wavelength, OTN switching, MPLS label switching, whatever. So this is basically showing the characteristics again a little bit more clearly. So from a control plane point of view, it just looks like a router network, a star network, but that's just the control plane point of view. And we propose to use the multi-protocol BGP, the RSVP DE, and the MLDP. And that's the same as in seamless MPLS. From the data plane point of view, we propose here to have a full mesh between the routers and a multi-layer optimized transport, because that is still necessary to, if you want to build really cost-efficient and green networks. So, and yeah, these are the different views of the network, so this is pretty simple. If we look now into the controller architecture, you can see here two sides. The left-hand side, that is what you would build for transport anyway. Yeah, and you have here a centralized controller with topology manager, the network controller, where you can also realize, of course, OpenFlow interface, which we haven't done yet. Resource discovery, multi-layer optimized traffic engineering, topology database, and so on. And on top of this, some applications, for example, layer 1, layer 2, layer 3 VPN services, whatsoever. This is basically reuses a lot of available software packages. Yeah, because we have these available, these software packages in our network management system and in our planning tools. Yeah, and partly for real multi-layer optimization is still a separate software package, but it's available. So then on the other hand, you just need to have these realize these protocol stacks in a centralized way. We propose here the Quagga routing suite to realize these protocols for signaling between the clients and the core transport. yeah, the SDN controller, basically. Yes, not more to say to that. What is our current development status and demos which we have done? So this SDN platform already exists, as I told you. We call it currently Intelligent Optical Control. And the control layer, as I also told you just before, mainly then consists of software packages of the TNMS and our planning tool, which is TransConnect, which has a lot of functionality. So what we have currently is this system basically available, and we are actually building it for a very large operator, for a very large network. Yeah. So first releases have been delivered already, just for the DWDM layer. Yeah, just controlling the DWDM layer. Other layers will follow. Yeah, and the purpose behind it is to provide fully automated end-to-end workflows to make planning, installation, and management more efficient and reduce the times there. And we have done there some benchmarks. The times to plan and install new services can really significantly reduce by up to 90%. Yeah. So this is the initial start-off of this project. It didn't start off as SDN. It started off as this workflow system. And of course, then we need also to make sure that all people collaborating in network planning and operation are mutually synchronized. And if you look there at different, especially in large operators, on the workflow processes, that seems to be easy, but it isn't really. Yeah. So there's a lot of functionality behind for this end-to-end process, which I will show you in a minute. Yeah. Now, using this IOC, of course, you can build on top of it applications, and you can build the applications in different ways. We have done here network virtualization application for the which we demoed also at the Optical Fiber Conference this year in where was it? Not sure. Anaheim, I think. Huh? Yeah, it was in Anaheim. Thank you. What the services to which would be provided is basically a virtual network consisting on the DWDM layer, so virtual wavelengths, consisting of dedicated transponders, wavelengths, and so on. Yeah, regenerators and so on. So this is what we did. This is shown here again a little bit more in detail. So the control layer basically takes the full control of the DWDM network, and then on top of, then from the on the applications layer, we have realized that to split this network into different parts, so different wavelengths for each section, different access to transponders, and so on, and allow this virtual network operator to give him the access rights to assigned resources, select resilience scheme, request new equipment, fault management, performance management of the assigned resources, and also rerouting the services among the resources which he has. So this we have demonstrated also. Well, this shows the overall benefits of such an approach, and we think this goes beyond at least the current focus of SDN, because it really looks at the end-to-end process. So from strategic capacity planning to network maintenance, but also things like spare part management, which are very important, especially when you have this high priced 100G or in future 400G, whatever, 1 terabit interfaces. Yeah, so this makes a lot of sense. And that was basically the initial intent also of the customer to get here such an end-to-end system in place, fully automatic workflows. So now, of course, if you look at this structure, you can extend the structure very simple, because what we did now before is just via a web-based GUI to request new services. That is what was the application before. Now, what is the issue when you want to integrate routers or want to have signaled requests? Yeah, so signaled requests from the client, not having the requests for a client connection via a web-based GUI, but just letting the client to request services itself. Then, of course, you can follow this approach of the GMPLS UNI or UNI Plus, or ENNI as we call it now, which we also have under development, basically coming also from a different stream, so to better interwork with routers and also let routers to have colored interfaces and work directly into our DWDM system. And the service control could here be this GMPLS ENNI, which is basically a UNI Plus and allows to convey some routing information from the network to the client. So, for example, shared risk-linked resources. Yeah. Service type here would be also, of course, a virtual network consisting of dedicated and so on, layer 1, layer 2 transport and switching resources. So this is still the standard application, and now you just have to go one step further and say, okay, now I do the same thing for the router with IP-MPLS NNI, and then you need to have the IP-MPLS functionality also in the SDN controller. Of course, it's not easy, but it's possible. And you just, as I told you, you just need to do the RSVP, TE signaling, multi-protocol, BGP routing, MLDP routing. And this approach, of course, has a big advantage that you do not need to rebuild your whole network. You just can rebuild the core, or maybe also rebuild the core in parts. Yeah. So it's an evolutionary and not a revolutionary approach. You do not need to look at all the installed routing functionality, and do not need to replace PE routers and so on. Yeah. So this is the idea behind it. Well, still some bit to go for this. Nevertheless, if we look at what we have done on this in NSN, we have many activities and proof of concepts jointly with previous NSN, because they are also looking at that. So we, on the one hand side, of course, we as Corient also are now a member in ONF, and NSN is a member as well, driving carrier-grade open flow interfaces. We have virtualized network functionality is more a topic for Nokia Siemens networks in the mobile broadband for virtual eNode B, virtualized evolved packet cores issues. So there they are looking heavily, and this is maybe a trend also to come. So and also virtualized gateways. So we would be looking more at virtual backhaul, which is then falling into our category. Well, it's metro, not core network, but it falls in the transport category. And we have also used here Open vSwitches, and well, you can read it yourself. Not in a position to explain this picture. Yeah, if you look at this Quagga routing daemon, you can see here a demo which has mainly been done by NSN. For an end-to-end network, and here you can see the evolved packet core user plane. You look only onto this one, which communicates here with the routers via OSPF. These Open vSwitches have got some extension for GPRS, tunnel protocol terminations, some proprietary extensions, and they are controlled via OpenFlow, OpenFlow Plus because of the GTP extensions from an OpenFlow controller, which has been built by ourselves, and also the Quagga routing daemon has been used to communicate here between routers and these Open vSwitches. So this is possible. You can also read it in the literature. There's also some, don't have the references in my head, but there are a couple of references for centralized routing in the history. The beauty is that now here also there is some open software available. Well, that's it, what I wanted to tell. I'm well in my time, I hope. So just some summary final remarks. What we have done, we have proposed an approach to packet optical integration for core networks, which allows true multi-layer optimization in the full mesh of PE routers. This means consolidation of core routers, thus avoiding the problems of previous more router-centric proposals. We have shown that the SDN controller for this approach makes reuse of available transport software packages and allows a phased development starting with layer 0 to layer 2 services. And the required centralized routing functionality can be based on open source software. Many key components of our proposals already exist. Others have been demonstrated, and on the network level, our approach is in line with seamless MPLS. That's it. Thank you. Questions?
Okay, thanks very much. So there is time for, I don't know if the microphone works, but there is time for questions. So who wants to be brave and start with a question? I'll give you some time to be brave. I'll do
no
one
question means everyone agrees. That's fine.
Yeah. I have a question on my side then. Let's say if you have, you use the word SDN, and I assume that SDN must have some protocol on top of it. Let's say a northbound interface. Is that already defined? Are you part of the definition of that protocol, or?
Well, I'm not personally part of this. I think in the standardization, they are looking at it, how to combine different SDN controllers. And we have just recently started with one operator, not the one where we provide the IOC, but another one, to define here northbound interfaces to other SDN controllers, because they need to work together. So when you have, for example, data center connections and you control the data centers with SDN, you would like to have an interface to the optical control, and this is exactly what we are doing right now. But I think it's also a topic of the standardization, as far as I know.
Yeah. Other questions? No? Then I want to thank again Manfred for his presentation. Thank you. Now we get to the second presentation from Ronald van der Pol. And he's working for SurfNet. I think he also worked for Zara also in Amsterdam. And what Ronald is going to talk about is about multipath TCP. And that together with the OpenFlow protocol. I think it has some relation with the talk we had this morning about from Stephen Wolf about big data and how do you transport that from A to B, because sometimes you want to get access to that data. And I think multipath TCP might be an option for that. I have to keep on talking, I assume. And there are, of course, lots of other things in the past, and Ronald will talk a little bit about what things were there in the past. So what are the ideas about multipath TCP? And there has been done a few experiments with multipath TCP, at least 3, and he's going to talk about 3 of them. One, do I have to do your talk or not? One is about the glyph, the other one is a supercomputer, I think 2012, you can nod if that's true. And the other one is very, very recent. It's only there for perhaps a few hours, I think. That is the 100 gigabit link that is here towards Maastricht. So it's very hot off the press data, but he will also do that, but I think Michael will also say something about that hot off the press data. So Ronald.
You deserve an applause.
The floor is yours.
Yeah, thank you for this introduction. I feel honored. Okay. Yeah. I will be presenting our experiences with OpenFlow tests, as Victor explained. We have done a couple of demonstrations last year, and we also have a demonstration tomorrow. The theme of one of the themes of this Torina networking conference is innovating together, and I think this is exactly what we are doing. It's a partnership of a couple of companies all over the world. It's Caltech, who is a partner in the USA. iCare, part of Northwestern University. NL Labs in the Netherlands, the Technical University of Delft, also in the Netherlands, and also the Université Catholique Louvain in Belgium. So what will I present? I will start with explaining why we do multipathing. Part of what we do is MPTCP, multipath TCP. I will explain how that works. And then some results of our demos. As Victor already said, I started working on this at Zara in 2010. That was, we also looked at a single server, what you could do, how much data you could stream from that. At that time, we used multiple 10 gig interfaces. We used UDP streams, and we were streaming video to a tiled panel, large display. We did 4 times 10, 6 times 10, and also 2 times 40. So why are we doing this? It's all about big data. Lots of data out there, still growing exponentially, and these data sets need to be copied over the network, and we need to use all available bandwidth simultaneously to have the shortest time of transmitting data. We are also reaching the Shannon limit. Steve already said something about that this morning. I will have some slides about that. And we also think it's the next logical step. If you look at computing, networking, especially computing, we started with, if you look at the server, we started with multiple disks in a server. Then we put multiple CPUs, multiple cores in a server. And multiple network interfaces is the next logical step to get many data out of the server. little bit about big data and the reasons, a couple of reasons. This is about DNA sequencing, the price of a DNA sequence. 10 years ago, that costs $10,000 US dollars, and now it costs a dime. So a huge decrease in cost of doing DNA sequencing. This is the genome online database, the amount of projects, and that is growing exponentially. Another reason, the Shannon limit. We are reaching that limit with optical fiber. And there is now a trade-off between bandwidth, the reach, how far you can go with your signal, and the cost, of course. You can have high bandwidth and large reach, but that costs a lot. And the really high reaches, high bandwidth, are only done in the labs at the moment. So this is the Shannon limit, not the Shannon limit. This basically says, this is a measure of the distance. This is the farther you go to the left. How do I explain it? To the left, you can go farther with your signal. And vertically is basically the speed of the signal. So what this means, for example, for 100 gig, this is a plot of Shanna equipment. This was the previous generation, and the newest generation has a higher reach. So they can go further for the same amount of bandwidth. So that's one thing you can do, or you can use the same technology, but not have farther reach, but go higher in bandwidth. So that's the trade-off. And this red line, that's the line you cannot cross. So you can go to maybe 400 with this this amount of distance, but at some time you will hit this limit. So one of the technologies we are using is multipath TCP. It's a working group in the ITF, has been active for a couple of years now, and there's currently, for several years, there's a Linux implementation, and since this year there's also a FreeBSD implementation. And what it does is load balancing over multiple interfaces, multiple paths. MPTCP just assumes there are various paths in the network. It doesn't set up these paths. It just uses what is available. So you have a multi-homed server, and it uses all the interfaces on that server. Or if you have a phone, you have Wi-Fi and 3G, it uses both interfaces. So it's all about load balancing, and you can do load balancing either in a network or at the end hosts. If you look at load balancing in the end hosts, it's usually one example is equal cost multipath routing, and then you always have to deal with hashes. You calculate a hash, and each flow is hashed to one of the interfaces or one of the routes. And that works if you have many flows, but if you have only a few flows or one flows, as you have in eScience data, then the hashes don't work that good anymore. That flow would, if you have two flows, the possibility that they are both mapped on the same interface is too high. So that's one of the reasons we started looking at MPTCP, because that that is a single flow. It works for a single flow. It can also handle links of different speeds, and it also really load balances. has congestion control, and it puts the load on the least congested links. This is a comparison between traditional TCP and multipath TCP. Traditional TCP to the left, you have the application TCP stack. The byte stream of the application is split up in segments, handed to the IP stack, and put on the interface. To the right is MPTCP. You still have the application byte stream from the application to the MPTCP layer. The MPTCP layer segments and spreads the load, spreads the segments across all the subflows. For each interface there's a subflow. And that is handed to the IP stack. The nice thing about this is that to the application, the interface looks just like a normal TCP interface. It's a normal socket API, no changes needed to the application. And to the network, to the IP layer, it's just normal IP packets. In the network, you don't see it's MPTCP. The only thing you see is in the TCP header. It's a TCP header option. There is an header option for MPTCP. So what does MPTCP do? As I said, it's the normal socket API. It splits the byte stream and sends it across the subflows. And what MPTCP also does is path handling. So setting up multiple paths. This is done initially. There's a normal MPTCP session on one of the interfaces is set up. Sending MPTCP sets a header option that it's MPTCP capable. It gets an egg. And in that egg, if the other server is also MPTCP capable, in that egg, the header option that receiving server is also MPTCP capable is set. So both are now know that both can do MPTCP, and then additional interfaces are exchanged so that they can use all the interfaces between them, and hopefully that means also multiple paths. But that's basically an assumption. That's what MPTCP assumes, that there is linked disjoint paths. So that's the packet management, is the packet scheduling, splitting the segments, splitting up the byte stream into segments and reassembly at the receiving side. And there's also congestion control on each of the subflows. There's the normal TCP congestion control, and when the link is busy, one of the other subflows is used. Another technology we are using is OpenFlow, and how we can set up multiple paths in a network using OpenFlow. And the next presentation will go into detail about that. So we did a couple of demonstrations with these technologies. The Glyph working shop last October in Chicago. Supercomputing last year, November, in Salt Lake City. And we also have a demo this week. There's a demo slot tomorrow afternoon at 4:30. So the Glyph demo, we had this topology. These are all the OpenFlow switches, PK8 3290 OpenFlow switches, a server in Geneva, a server in Chicago at the venue, and we also had a server in Amsterdam, and various links between them. There was also an OpenFlow switch in Geneva at CERN, where one of the Caltech POPs is. And all these overflow switches were controlled by a controller, an application, and multiple paths were configured through this topology. We used iPerf to send data from Geneva to Chicago. We used 4 links, 4 10 gig links of the ACE link, transatlantic link, USL at CNET link, also transatlantic, and a SurfNet link. Sorry. But we had quite some problems at that demo. We had a lot of packet loss on the wide area links. And we also saw some weird behavior of the OpenFlow switches. For example, MTU problems. We started with when we increased the packet size up to the MTU. At one point, it didn't work anymore, which is normal, of course, if you exceed the MTU. But in this case, it also stopped working below the MTU. But the strange thing was that if you then decrease the packet, it still didn't work. And only when you sent a really small packet, then it started working again. These were the problems we had at Glyph. What you also need to do is tune your server, of course. Use jumbo frames. Have all the network interfaces be jumbo frames capable. You have to send large packets, 9,000 bytes, large buffers at the servers, sending and receiving server. Yeah, and all these things, although we didn't, we only got, as it says here, about 1 gigabit per second over 4 10 gigabit Ethernet links. We learned a lot. Especially, the debugging also of OpenFlow networks, which is quite different than normal networks. And also because this was also a corporation with 3 different companies, 3 different domains, time zones that are 6-7 hours away. That makes debugging also quite difficult. And then, of course, you also had the providers of the links, SurfNet, ACE, etc. And there was a lot of communication needed, debugging needed. So next demonstration was supercomputing, November last year. We had a similar setup. Again, we streamed from, we used iPerf to send data from CERN at Geneva via Netherlight in Amsterdam. There were 2 OpenFlow switches over there. There was 1 OpenFlow switch at Geneva, server at Geneva. And we had a couple of, 4 10 gig links and 2 1 gig links. It went, some of them went via, or all of them went via Starlight in Chicago, up to the show floor at Salt Lake City. And at the show floor, there were 3 partners, SurfNet, SurfSara, iCare, and Caltech. They each had their own booth with an OpenFlow switch, and there was an interconnection between all the booths, and also the wide area links towards Europe were coming to those booths. So that was also a quite complicated setup. Also, lots of wide area links. This is the OpenFlow topology, OpenFlow switch in Geneva, OpenFlow switches in Amsterdam, in Chicago, and at the show floor. And currently we are using 1 OpenFlow switch, OpenFlow controller, and 1 application to control this network. Because at the moment we are still investigating the technology at a later stage. This, of course, has to be, each domain has to be its own controller. But that's not part of the current demonstrations yet. So unfortunately, at supercomputing, we had similar problems. 2 of the 10 gig links had packet loss. A third one we didn't get it working at all. So at one time we started using the link between Amsterdam and Geneva only. On that link, at that time, we also had packet loss on one of the links. And well, MPTCP did its work. It used a link which didn't have packet loss. And it didn't use the other link because yeah, packet loss is the same as congestion for the congestion control algorithms. So basically only one 10 gig was used. And we got about 9 gigabits per second over that link. So that was an improvement. We also built a monitoring website at Zara. Basically, the topology and the paths, the overflow paths through the network were shown in colored links. This was live traffic. It refreshed every second, so you could really see how the flows. Each flow has its own color and stacked in this picture. And then we could could monitor the throughput. It was quite useful. This is an example of Amsterdam to Geneva over 2 times 10 when we solved the packet loss. It was later last year. What you see is we had 4 paths, but basically it was because it's only 2 links between Amsterdam and Geneva. There's only 2 link disjoint paths. We configured 4 paths, but they were partly overlapping. So this is what you were seeing at the beginning. This is when we started the iPerf. It started using this link or this path, mostly this path, and then it's switched over to mainly this path and a little bit of these 2 paths. And at the end, it took longer than we expected, but after some time it flattened out, and basically the 2 link disjoint paths were used. And that is this situation. So the 2 link disjoint paths between Amsterdam and Geneva were used. It was 2 times 10, so you would expect this is 20 gigabits per second. And this is 15. So this was late last year. We reached about 14 gigabits per second. We are now up to 17 gigabits per second on this setup. So finally, the TNC demonstration. Hopefully we get it running tomorrow for the demonstration. Guess what? We also had packet loss, which was solved 2 days ago. So yesterday, some fibers were cleaned yesterday. So since, well, I say yesterday US time, middle in the night, local time here. Many people worked during the night, and we are grateful for them. They solved the problem, was some dirty fibers, and packet loss has been solved now. A little bit about our topology. This is the show floor, server at the show floor, overflow switches at the show floor, and we are using the 100 gig towards mainland in New York. Over 2 links by ESNet. We are allowed to use 40 gigabit of traffic on each link. So we have 2 times 40. There's also 2 times 40 on the server. So basically on the 100 gig link we will be streaming 2 times 40. Openflow switch in Chicago. Also an iCare Openflow switch in Chicago and a server in Chicago. Also, just like the server over here, 2x40 and 2x10. We also have a 10 gig circuit via USLTnet and a 10 gig circuit via the ACE project. We also have a poster downstairs. You can look at this topology. This is basically the same. Maastricht, Amsterdam, 2 Openflow switches, mainland Chicago. And the blue line is the 100 gig link. The ESNet links are also 100 gig, but we use 40 gig on each. This is our server. 2x10 at the top and 2x40 at the bottom. 2x40 go to the Openflow switch and then to the over here to the Juniper and then to mainland. And 2x10 go directly downstairs to mainland. No, sorry, to Amsterdam. This is the Openflow switch we are using, PK8 3920. Specs of the Supermicro server: 2 Xeon processors, 64 gigabytes of memory, disk for the operating system. There's 3 RAID controllers, a couple of SSD disks, and 3 40 gig Mellanox cards. And a server like this costs only 8,000 euro. Without the disks cost another, I don't know. Back then we bought them, 2 years ago we bought them for around 9,000 euro. They're cheaper and much faster now. But we used, for the time being, we are using the old disks. Switches are PK8 switches. We use a couple of 1 gig switches, a couple of 10 gig switches with 40 gig interfaces, and also a Dell switch with which has 32 gigabit Ethernet interfaces. So hopefully we get the demo running. We still have some performance problems at the moment. We have a demo scheduled at 4:30 in the afternoon at the Surf booth. And that's what I had to present to you.
Thanks very much, Ronald. So again, there are questions. Oh, multiple questions.
It seems like
Wait. I think you need a microphone. Keep on talking.
It seems like half-length skew would produce similar problems in reassembling the TCP flow that out-of-order packet delivery does with a single IP flow.
Yeah, you need a large buffer at the receiving side.
At 40 gigabits, it would have to be a large buffer.
Yes, indeed. Yeah.
Right, I mean, if there's very much skew, you're going to run out of buffer space, right?
Yeah, and that's one of the things we will find out in this demo. If you look at the differences in round trip time, it's about between 115 milliseconds and 130, I think. So it's not that different. So much difference in round trip time.
Well, at 40 gigabits, you can deliver a lot of bits in 15 milliseconds.
Yeah, that's true. Yeah.
Oh wait, I think this one here was first. Please.
If you are using 4 interfaces on client and maybe on server, do they use the same IP address or different IP addresses?
Different.
So that means that you also need, if you have that the application has to know about the
No.
destination IP addresses.
No,
it's not only normal DNS anymore.
No. That for the application, it looks like just one TCP session. It's the application opens a socket to one of the interfaces of the other server. If the other server has multiple interfaces, you get, for example, 4 interfaces, you get 4 IP addresses, 4 IPv6 addresses. You choose one of them, set up a TCP session to that IP address, and if both are MPTCP capable, the kernel, the MPTCP, the networking stack, MPTCP networking stack, sets up the additional interfaces and flows. But the application thinks it's just talking to this one IP address.
So my question is, in your opinion, does it make sense to extend the MPTCP stack to express more complex constraints, like, for example, not just looking at congestion, but latency and cost, perhaps, something like that?
Yeah, if you look at the example I gave about Wi-Fi and 3G, in that situation, it would make sense that you not only look at congestion but also at cost. You would prefer to use Wi-Fi, mainly Wi-Fi, and use the 3G only if you really need it. So yes.
Yeah, Roland, that would be in the API, and I don't know how that developed, right? Because there are many policy things you can do. You can decide which of the IP addresses you're going to use for a particular session, for example.
Yes. Yeah.
How has that developed recently? I haven't looked.
I don't think there's active work on that at the moment, but maybe there's 2 other frequent IGF goers, Benno and no?
No, there's no work.
Okay. Tim, you have an... okay. Maybe it's a follow. Do you have a follow-up on this question, or? No. Okay. Yeah. Okay. Yeah.
Okay. So if there are different round trip times on the different streams, so what is actually the processor load for working with such a multi-TCP stack? So I would somehow expect that the more differences there are in round trip times, the more CPU load it will take for the processor. Can you say something about in general and in specifically the processor load?
Yeah, not much. In general, I agree with you. We only reached, as I showed, 17 gigabits per second in the best of our experiments, and the processor could handle that, but we have not been able to do really large, and also that was 2 links with almost no difference in round trip time.
Yeah, well, it would be interesting to have a number of different round trip time differences and then see what the processor load does, if it stays constant or somehow also has an influence.
Yeah. We had a student last year who looked at several of these things, but we need to look. There's still a lot of work to be done.
Oh, a short comment on the question. Université Catholique Louvain, they did a test with 3G and Wi-Fi. So you have a difference with round trip times, etc. And well, the bandwidth not that high, of course. So, but it dealt fairly well with this difference in media types.
Yeah, but still, then you want to compare it with a single stream. What the CPU load? So I would like to compare a single stream TCP, what the multi-TCP protocol stack does on the processor, compare single stream, and what if there are more differences. But there's always room for further research.
Yeah, Tim.
Yeah, thanks. Hi. It seems you used OpenFlow essentially just to provision the test bed. Do you see it as being a future thing to actually have a protocol like MTCP be able to control the network to set up those?
That's a
parts?
very good question and introduction to the next speaker.
Oh, okay, I hadn't looked at that.
That is great.
The answer is yes.
Good. I think it's work under progress. I think the fact that people have to work even during the night to get links working is a good achievement. I'm glad that these kind of things of innovation are happening. So I want to give another thanks to Ronald also for staying up long. So. Okay, now we get Michael from CERN. He will talk a little bit of the ideas also, or let's say mentioned already by Ronald. He will go a little bit more deeper into the open flow ideas. So he will talk about the open flow protocol a little bit, but also he will go about the Olympus project. And that's perhaps you can better say yourself where it stands for. And perhaps it's there somewhere, but I would say the floor is yours. And
yeah, thank you very much. And the mic is also working. Yeah, I'm Michael. I'm actually working for Caltech. I'm only based at CERN, so I'm not working for CERN. That's always confusing to people. And I'm going to present our work on multipath switching and wide area networks using OpenFlow, and that's joint work with my colleagues at Caltech and also with Ronald and a bunch of other guys that contributed in various ways to that project, like ESNet and iCare, for example. So a short outline to the talk. I will give an introduction into the problems we are dealing with and the networking for the Big Bang Theory at CERN. And multipath technologies, Ronald already mentioned some, and then I will talk about the actual OLIMS project, OpenFlow link layer multipath switching. I will give a short introduction into SDN and OpenFlow and into the to the objectives and the OLIMS controller. And then I will talk about our current capabilities and the testbed results, and summary and outline. So I'm working for for Caltech's high energy physics network group, and we basically run USLHCnet. That's a network that transfers data from the LHC experiments at CERN to the US, and we participate in the LHC OPN, which connects CERN to 11 big data centers around the world, and the LHC Open Networking Environment, which then connects these 11 data centers to universities and smaller data centers also all around the world. We are dealing with large flows, with big data flows. So usually we transfer data sets from CERN that have the size of several terabytes, and we transfer them for a couple of hours or days. So we have a small number of flows, but they are large flows, and that's important to notice. Okay, why do we need multiple paths? Well, Ronald already addressed that issue, so I will go to that very quickly. We want to increase the capacity, we want to increase the resilience, we want to do load balancing in the network to use these multiple paths efficiently, and this can be basically used also to reduce your operational costs. And there are a couple of multipath technologies in the field. You can use ECMP, you can use link aggregations, but all of these techniques have some drawbacks. So in principle, they are not really flexible. You have to pre-configure them. They use static hashing algorithms. You cannot really choose which flow goes on which path. This depends on the vendor's implementation of the functionality, and you don't have any freedom to change that. Also, it's a distributed approach, so you usually take links into account, single links, and not the whole path. Every network component just chooses the next link and puts the flow to the next link. And that, of course, because it's distributed, it's hard to optimize globally. The OLMS project now tries to address these problems and the problems of limitations, especially in large-scale layer 2 networks. And we are using a centralized out-of-band control, the OpenFlow controller, to construct a multipath system that is robust. The advantage is that you just need OpenFlow capable equipment, nothing special. So compared, for example, to Trill or SPB, we are not modifying the packets or packet structure. You just can use OpenFlow. That's available by the switch. Almost every equipment today is OpenFlow capable, so just can use it. And then we want to remove the necessity, for example, of a tree structure in the network, achieved, for example, by the spanning tree protocol, because using that you cannot make use of multiple links or multiple paths in your network. You just use the shortest one, and that's basically it. And yeah, we want to allow per flow multipath switching on non-equal paths, so they don't need to be necessarily the same number of hops or the same capacity, can be totally random. And we want to support wide area links as we are running a network between Europe and the US. We want to have some solutions for there. So a short introduction to software-defined network and OpenFlow. I'm pretty sure most of you have seen this picture before. It's actually by Scott Schenker. And software-defined networks and OpenFlow, software-defined networks basically decouples the forwarding and the control plane in your network. So you have a bunch of devices, forwarding devices, switches, basically, that implement a protocol that they can be connected to a so-called network operation system. This protocol can be OpenFlow. It can be also everything else you can think of. So, but I'm using both terms, like software-defined networks and OpenFlow, in the same meaning. So even if it can be something different from OpenFlow. On top of the network operation system that provides you basic functionality, like talking to the switches and stuff like that, you can have applications that then deal with everything you think of, like spanning tree protocol, if you still want to have it, or BGP, or whatever you think. And whenever I see this picture, I think, okay, that's kind of fuzzy. So what does it actually mean, and why is software-defined network nice to have and good to have? One slight remark, I highlighted software-defined networks. If you want to deploy OpenFlow, SDN, something like that, you not only need to deal with the network equipment, you also have to deal with the software. So you need, in addition to the network engineer, someone who's able to read and write software. So you need a software engineer in addition, basically. At least today, because the controller and the controllers that are available are not mature enough that you just can deploy them. Okay, if we look at the evolution of networks over the last decades, we find that we had 10 megabits, and then 100 megabits, and gigabits, and now we have 100 gigabits, and tomorrow we will have terabit per second capability. That's actually kind of impressive, but it's also actually kind of boring, right? We just increase the capacity. Cool. That is the evolution in the forwarding plane. What about the evolution in the control plane? So if you look at a control plane in 1990, and you want to configure your switch there, you log into a CLI and configure your switch. That was like 25 years ago. What's the evolution there? Well, it's basically the same. I'm not saying that there is no innovation there. I mean, 1990 you had Telnet. Today you have SSH. So if we compare that to evolution, it means we start crawling, and now we are still crawling, but very securely. And I really think that software-defined networks and OpenFlow can make a difference here. It can simplify your network management, the control plane. It can reduce the complexity of your network. But what do you need for that? You need an open flow controller. And we developed the Olymps controller, which is based on Floodlight. Floodlight is a controller written in Java. It is very performant. It outperforms also C++ written controllers, so Java is really good here. It's supported by Big Switch. It's basically the core of the Big Switch commercial controller. However, it's open source under the Apache license, so you're free to use it and develop your own stuff. Floodlight already ships with a bunch of functionalities and applications, so like link discovery. Out of the link discovery, it calculates the topology and also a spanning tree. This one? I can use this one. If it works, yes, perfect. Okay. Yeah, it comes with a bunch of applications. So link discovery, it calculates topology. It also has simple packet forwarding and a learning switch, for example. And here you can see the basic architecture where you have the core modules written in Java. You have some applications that are also contributed by the community, like the firewall, for example. And you have a northbound API where you have a REST interface, and you can easily write your applications in every language you would like to, like Python, for example. This controller still lacks a lot of functionality you want to have if you want to deploy it into a real network. But it's a good start. And we extended the functionalities and added new features. Like, for example, if you want to have multiple paths and you want to have a really highly meshed network, you want to avoid that there are broadcasts in the network going around and create loops quite easily. So we have a broadcast filter. We do some tricks to prevent loops. We have a proxy ARP that deals with with ARP requests and stuff like that. We also implemented flow cache servers so that the controller basically knows about the state, about all the flows that are in the network, and that I can query a database, memory-based database, just to get the information directly from the controller. I can read statistics. These are made available to the controller. Of course, we have a multipath computation. So we calculate the multiple paths and a load balancing. And we had some additional functionalities or tools like a CLI. And we already put some effort into the controller that it helps us to debug the network. Guess why? And learned from TNC this year, we need to extend that. So we still need more functionality in the controller that helps us to debug things that are going on in the network. So the link discovery, for example, just uses LLDP packets that are sent from each switch to the next switch, and modified LLDP packets so that if you have non-open flow equipment in between, the LLDP packets usually are consumed. So we changed them a little bit. They have a different data link layer type, and then they go through even if there's non-open flow equipment in the path. That's especially important in our network because we have the open flow switches at the edges of our network, but we have, of course, non-open flow switches and routers and stuff like that in between, and we create VLANs between the open flow switches to have some kind of open flow overlay network where we can run our tests in. Based on this information, Floodlight already creates a topology view, so you basically have a connectivity graph representation in the controller. And this can also be displayed or pictured in a graphical user interface. So this is the picture of our topology that we have here at TNC with all the open flow switches or Ronald presented previously. Also important Floodlight uses the notion of open flow islands. These are open flow switches that are directly connected with no other equipment in between. To connect these open flow islands, so if you have non-open flow equipment in between, that's kind of tricky, and it's actually not allowed by the original floodlight, so we also did some modifications and tricks to connect, to have multiple paths through non-open flow equipment. Yeah, and then the OLMS controller or the OLMS extension uses this topology information to calculate multiple paths and do actually the forwarding. And yeah, as I said before, we also allow multiple paths through non-open flow equipment. The multipath computation, it's actually not that hard to do. Once you have the connectivity graph, you can just use your favorite graph theory algorithm to calculate the multiple paths. Like Dijkstra's algorithm to get the shortest path might not be the best option, because once you do that in exactly this topology, you can see that you only find one path. So there are better algorithms like Sorball's where you can really find the multiple paths in the network. But as I said, it's actually not that difficult. Once you have everything around that, if you have the path, if you have the links, if your controller knows about all this stuff, you just can calculate it. However, the path can have multiple characteristics. You can have multiple capacities on the path and delays and packet loss, I don't know. So what you actually want to do is a load balancing, or you want to have an algorithm that makes the decision which is the best path and where do I need to map my new flow to. And here you can also think about various algorithms that do that. For example, you just pick one path randomly. That is basically done by ECMP, and you have a hashing, and the new flow is mapped to a path, totally random. You can also do round robin here. This is not possible with the current equipment you have, but using OpenFlow on the controller, you can just select the next path for the next flow. That avoids uneven distributions, as Ronald already mentioned as well, is that with ECMP, and if you have only a low number of flows, it can easily happen that all the flows go to one link. Even though you have more, or one path, even though you have more paths than that, you just can end up with that. You can then try to configure it manually, that this is not happening and stuff like that, but then it becomes really, really ugly and painful, and if you want to change something, it's a mess. So here we can use round robin to avoid that. However, this does not avoid or prevent uneven utilization. You can also do other things like number of flow based path selection. So you know the number of flows that are already on that path, and you choose the one that has the less number of flows. That's a really small experiment I did right before TNC. I just used a topology where I had 4 linked disjoint paths, which basically had the same characteristics. That is in terms of capacity. So all the paths had 10 gigabit per second capacity, with a different number of hops. And then I used several TCP streams generated by iPerf, and each TCP stream transferred 5 gigabyte of data. And then I just, here on this graph, you can see the number of parallel streams or flows increasing, and the time the average time that it took to transfer the data. And you can see that the more flows I have, the higher the transmission time. And since I selected the path randomly, also the transmission time varies a lot. You can see the maximum, the minimum, the average, and the what's it called? I don't know. Something else. Confidence intervals. Now, if you're lucky, you get a good performance with this approach. If you're not that lucky, you just choose the same path for 2 or more flows, and then it takes longer to transfer the data. If you use the approach of looking to the path and take the link utilization and then choose the path that has the lowest link utilization, you always get the path that is best for your transport. And that's really a simple scenario. I know you can have multiple different flow characteristics and stuff like that, then it gets more complicated, but you can see that you can benefit from that, from things you can do in a central controller instance to decide what is best for the next flow. And now, once you have that, you can start doing all the cool stuff we are going to do in the next week. You can easily implement any load distribution or algorithm you can think of. You can use all the information that is available at the controller, like the capacity, of course, link utilization. You can try to estimate the available bandwidth. You can take the number of hops into account, the latency. And something we want to try out, we did not do that yet, in the process of doing it, we want to have an application that tells us how much data it's going to transfer, and then we can also take this into account and see if we can improve the utilization of the network. What we also can do already is we can move flows seamlessly. So I can decide, okay, this flow on this path is not good anymore. I want to put it on another path. So I just can say, hey, controller, please move this flow to a different path. And then this is done seamlessly, depending on the number of hops and the path characteristics I choose. TCP is almost not affected by this movement. And in the future, we want to do this dynamically, based on real-time feedback, like topology changes. That's obvious. If you have a fiber cut or something, your topology changes. You want to react to that. But also congestion notification. If one link is congested, I can remove paths. I can move paths to different flows to different paths. Something we want to do with ESNet is we want to extend the VLAN integration in the controller, and we want to be able to create circuits using the Oscars interface automatically from the controller. That's just basically for convenience, so that we can create this topologies more easy directly from the controller. And the controller then also takes care that that all the flows that go into that network are directly mapped correctly to the VLANs that are there in the dynamic circuit system. MPTCP, of course, we are doing that together with Ronald. And one idea we have here is that we also make the controller aware of MPTCP flows and react or respond to that. So the first packet from an MPTCP stream has MPTCP options set in his header, and this first packet goes to the controller. I can make a deep packet inspection, basically look at the header, see that it's MPTCP, and then I can respond to that, especially for MPTCP, and then I can select disjoint paths, something like that. Also, if we do load balancing and congestion control in the network itself, it becomes a dynamic system. So it will be interesting to see how it reacts if you have a TCP that also does congestion control, and what happens if you actually move a flow to a different path. Is it really good to do that, or is it something that does not really work? We don't know that yet, so we will investigate that in the future. Okay, just a short summary of what I've presented. So the OLMS project is to study and implement multipathing in wide area networks based on OpenFlow. What we can do is we can do multipath computation. We can use per flow load balancing already. We can also seamlessly move flows from one path to another. Now we need to use the CLI to do that manually. We want to do that automatically. And we're heading towards an interface with Oscars, and surely an API and an interaction with applications. Thank you very much, and I'm happy to answer questions.
Thanks, Miguel, for this interesting talk. Are there questions? Okay, microphone.
So I wonder, in the circumstance that you're using MTCP underneath one of the application level parallel flow devices, systems like grid FTP or even FTT, I wonder if you get into stability problems in the link utilization algorithms when you have a lot of parallel flows that are then divided into what seem to be independent flows at the MTCP level, but in fact are not independent.
Yeah, that's an interesting thing to look at. I mean, we are not in a stage that we have looked at that, but that is something we are interested in, definitely. So stability is an issue.
Okay. Other questions? Tim, your question was answered? Yeah, I see there two hands.
I recall in the beginning of MPTCP, they even said that if the paths you choose end up accidentally converging and diverging in the network, that you can interfere with yourself and get instability as well.
Pardon, the last part?
You can cause yourself instability if your paths are crossing in the network.
So as far as I understood is that if MPTCP streams share the same link, they have a special version of their congestion control algorithm, because they don't want to be unfair to other TCP flows. So, pardon? Or themselves, yeah. And what we can do, especially if we have an application that specifically addresses MPTCP, we can make sure that there are no overlapping paths in the network. So for this specific flow, or MPTCP multiple flows.
So hi, I was wondering whether you tested this with different traffic patterns. Are you going to
Yes.
see how it reacts? Okay. Good.
So this was really a very easy test a week before TNC, and I used 5 gigabyte files transferred over the link. So it has the same, basically the same characteristics.
So you have one sender, one receiver. So, and I was wondering, when you have more senders, more receivers, and then you have different data
Attention,
rates.
please. All evening
gonna
BOFs and the Cisco Symposium are starting downstairs at 6 p.m. Thank you.
You're
Thanks.
welcome. So I was wondering what happens when you have varsity traffic, like how the controller and OpenFlow reacts.
Yeah. So what would be interesting is if you have multiple instances of sender and receiver that want to transfer different file sizes, and if you not only have long-lived flows but also mixtures with long-lived and short-lived flows, and that's on the to-do list.
Okay, I want to wrap it up. I think we went from optical to layer 2. SDN, OpenFlow were touched upon, so experiments that are going on at this very moment, so that's really good work. And after, I think, hopefully next year, there will be also the interaction with the application and see how that works, and if the networks don't go up and down because of all these oscillations that will happen. Before really closing and giving everybody again, or the presenters another applause, I want to say or perhaps you have seen it already, there are BOFs, so don't forget to go to the BOFs. The day is not over yet. There are also posters of students. Please give them attention and vote for them, for the best ones at least. And the other thing that I would like to say, there is also an open space session. It's at the end of this conference. For me, it's part of the conference. So make sure that you have your ideas, even if they are vague, put them on the board over there and make sure that you and others are going to talk about the future of the internet. So it's for us good. Doesn't have to be only technology, can also be, of course, of all these high-level political things. But okay, thanks again for the presenters, and have a good day.